In this video, I want to discuss the force of gravity a little bit more in detail. In previous videos, we've talked about the force of gravity when you're on a flat surface or an inclined surface, and we've discussed how if you have a box on a flat surface, a box or a sphere or a ball or a car, whatever the case may be, the first force you should always write down is the force of gravity, which is calculated by just simply taking the product of mass times acceleration of gravity. And of course, ask yourself the question, well, which way is the force of gravity pushing me? And the force of gravity is always pulling you and pushing you towards the center of the planet. And if the surface is strong enough, it's going to prevent the box from going down, which means that the surface is exerting a force upwards. And we discussed this last time, and we said that's called the normal force, the force that the surface exerts on the box so that the box stays in equilibrium on the y-axis. In this particular case, the normal force will be the same as the force of gravity. Now, some people may think that this is an example of Newton's third law. Newton's third law is every action has an equal and opposite reaction. This is not actually an example of Newton's third law, because Newton's third law also said that the two forces, the equal and opposite forces, have to be exerted on separate objects. Over here, both of these forces are being exerted on the same object. So this is not an example of Newton's third law, even though these forces look like they're equal and opposite. What is an example of Newton's third law is this. If you step back a little bit further and you see this is the Earth, this is the planet you're on, this is the center of the planet, and this is the object that we're discussing. So what's happening over here, because the Earth has mass, or the planet has mass, and the object has mass, these objects trade gravitons with each other constantly. It's like playing a game of catch. So they're trading gravitons with each other, and that trade of gravitons is what generates the force of gravity. So what happens is that the Earth pulls on the object towards the center of the Earth, and the object pulls on the Earth with the same amount of force. They're both pulling on each other. It's the object that ends up moving because the object is smaller. When you toss the object up in the air, it's the object that comes down towards the Earth, as opposed to seeing that the Earth goes up towards the object. Because the object is the smaller mass, it's the one that's going to move. But the object is exerting a force on the planet, which is the same force as the planet is exerting on the object. These are equal and opposite forces, and this is an example of Newton's third law. Now, this force of gravity can be calculated by using mass times acceleration of gravity, if you know what the acceleration of gravity is. So if you're on the surface of the planet, you can use 9.8. But if you lift this object up, 1,000 meters up, 2,000 meters up, 3,000 meters up, then you're no longer at the surface at sea level. You're not at sea level, so you can't use 9.8 meters per second squared. You have to recalculate the acceleration of gravity. So there is another more precise equation for the force of gravity, and the force of gravity equation I'm going to put up here is more precise in calculating the force of gravity. It takes into account the mass of both objects. So mass 1 can be the mass of the planet, mass 2 can be the mass of the object. It takes into account the distance between the center of object 1 and the center of object 2. So object 2 is very tiny, so this distance is going to be insignificant. However, the distance to the center of object 1, which is the planet, is very significant. So take that into account. Keep in mind you need to know the distance between the center of object 1 all the way to the center of object 2. And then you have a gravitational constant here. This value will always be given to you. It's 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Now that I'm going to write it up here, this value is 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. And the reason why I'm writing it up here for you is because looking at the units for the constant reminds you what units should be used for your masses and for your distance. Because you have kilograms in here, that reminds you that your mass 1 and mass 2 both have to be in kilograms. Because you have meters in here, it reminds you that your distance has to be in meters. So keep that in mind. Look at the gravitational constants units and remind yourself, don't put grams in here, don't put centimeters or kilometers in here. Make sure the masses are in kilograms, make sure the distance is in meters. And you'll notice distance squared will cancel out. Meter squared will cancel out. Kilograms times kilograms gives you kilograms squared. That kilogram squared will cancel out with this kilogram squared, and all you'll be left with is newtons. And you need to be just left with newtons because you're calculating a force. Forces are calculated in newtons. The other important thing you've got to take away is, and this is what they're going to ask you in the AP exam, they want to know about relationships. So they're going to ask you a question and say, okay, if you have a planet, planet 1 and planet 2, and they're a certain distance apart, what happens when you increase the mass of one of those planets? So you have these two planets. Let's say this is planet 1, M1, this is planet 2, M2, and they're a certain distance away from each other. Let's call that R. And the question is that they both exert a force of gravity on each other. M1 is being pulled towards M2, and M2 is being pulled towards M1, equal amount of forces, opposite direction. And they may ask you a question, okay, what happens if you double the mass of M1? What happens if you take M1 and you replace it with a planet that has twice as mass, twice as more mass? So what will happen to the force of gravity? And you're going to say, well, if you increase the mass of object 1, the force of gravity between the two planets is going to double. So if you double the mass of M1, your force of gravity would double. Okay? If you double the mass of M1 and M2, then your force of gravity between the two planets is going to quadruple, because you're having a factor of 2 increase over here and a factor of 2 increase over here. So those two, that doubling the mass 1 and doubling the mass 2, is going to impact your final answer by 4 times. It's going to increase it by 4 times. And vice versa, they're going to ask you questions like, okay, what if you halved mass 1? If you took mass 1 and you replaced it with a planet whose mass was half as massive as the original planet, well, if mass 1 becomes half of what it originally was, then the force of gravity becomes half compared to the original situation. They're also going to ask you things like, what happens if you double the distance? Well, if you double the distance between the two planets, if you double the r, the force of gravity is going to decrease. You know that for sure, but by how much? So if you double the distance between the two planets, the impact it's going to have on the equation is that the answer is going to become 1/4 its original value, because whatever variable you're doubling is being squared. So if you double the distance between the two planets, the entire answer becomes 1/4 its original value. If you triple the distance between the two planets, the entire answer becomes 1/9 its original value, and so on and so forth. If you quadruple the distance between the two planets, the entire answer becomes 1/16 its original value. And if you have trouble understanding this, plug in numbers. So let's try that. Let's just make it very simple. We're just going to put in simple numbers in here. For gravitational constant, we're not going to plug in 6.67. We just want to see how much of an impact it'll make when we change the mass and the distance. So for now, we're just going to keep it simple. For the gravitational constant, we're going to plug in 1. For mass 1, we're going to plug in 1. For mass 2, we're going to plug in 1. And for distance, we're going to plug in 1. Simply, this comes out to be 1. So we're going to compare everything to 1. If they say, what happens if you double the mass of M1? Well, if you're going to double the mass of M1, your numbers are going to change, because your G is still going to be 1, but you're doubling the mass of M1, so instead of 1, they're saying make it 2, and you're keeping M2 the same, make that 1, and then your distance is still the same. So your final answer is going to become 2, which is twice as great as what it originally was. And if they say, okay, now let's say you double M2 as well, so they're saying double the mass of M1 and double the mass of M2. Well, if you double the mass of M2 compared to what it originally was, 2 times 2 is 4, so it's going to have an impact of 4 times greater. This force will be 4 times greater what it originally was. So if this was 1,000,000 newtons, or this was 1,000 newtons, this will come out to be 4 times that value. It will be 4,000,000 newtons, or 4,000 newtons. You can practice this by saying, okay, what happens if you double the distance? Well, if you're doubling the distance, remember it has to be squared. If you're doubling the distance, so instead of 1, you plug in a 2 in here. So instead of writing 1, let me write this a little bit larger. So instead of writing a 1 in here, you plug in a 2. Well, you notice 2 2s are 4 if you square it, so this becomes 1/4. This is 1/4 of what it originally was. If you triple the distance, instead of 1, you make it 3. 3 squared is 9. So this answer becomes 1/9 its original value. The purpose of me discussing this is because on the AP exam, they like asking you questions about relationships. If you change one variable, how does that impact the other variables? If you change one variable, how does that impact the final answer? So keep in mind the force of gravity equation. This is a more precise way of calculating it. This is a method to calculate the force of gravity if you know what the acceleration of gravity is. And if you don't know what the acceleration of gravity is, you can recalculate the acceleration of gravity. And how are you going to do that? Well, if you have an equation for the force of gravity and you have another equation for the force of gravity, smart thing to do is set them equal to each other. So this is object 1, mass, the Earth is mass 1, the object's mass 2. So in our equation over here, we're talking about mass 2. Same thing over here. Object 1 is the Earth, object 2 is the box. So if you have these two equations and you set them equal to each other, you say, okay, force of gravity equals force of gravity. That is this equation, this force of gravity is this equation. If you set them equal to each other, first things first, you're going to notice something drops out. Mass 2 drops out. Mass 2 cancels out. And what you derived is an equation to calculate the acceleration of gravity. Acceleration of gravity based on the mass of the planet. So mass of Earth in our particular situation, not the mass of the object, mass of the Earth. And how far are you from the center of the planet? So if you're at sea level, you're going to take into account the distance, the radius of the planet Earth. But if you're not at sea level, if you're 1,000 meters above or 2,000 meters above, you're going to have to take that into account also. You're going to have to take the total distance you are away from the center of the planet. And this will calculate the acceleration of gravity for you. And it won't be 9.8 if you get further and further away. This number is going to decrease. And if you can recalculate the acceleration of gravity, you can plug it back in here and use this equation to calculate the force of gravity. Or you can just go back to the more precise equation to calculate the force of gravity. So that was one thing I wanted to make sure I clarified. The other thing I wanted to make sure I clarified that this is not an example of Newton's third law. The normal force is not an example of Newton's third law. This is an example of Newton's third law, that the object exerts the same force on the Earth as the force exerts on the object. They're equal and they're opposite. And the third thing I wanted to clarify is that relationships are very important. So understand that if you change one variable in the equation, how does that change the entire answer for you? So if you double the mass 1, the entire answer doubles. If you double mass 1 and mass 2, the entire answer increases by 4 times. If you double the distance between the two planets but keep the masses the same, then the entire answer becomes 1/4 its original value. This was a quick discussion that follows up what we discussed in class about the force of gravity. I hope you found this useful. And if you have any questions, ask your physics teacher for more detail.